Now I'm going to prove, finally, Demorgan's laws for Boolean algebra. All right, now you've seen Demorgan's laws twice now. First, you saw it in symbolic logic, which said what? The negation of A and B is not A or not B, and the negation of A or B is not A and not B. You also saw it in the context of set theory, where we saw that the complement of A intersect B is A complement union B complement. Well, it's true in a Boolean algebra as well. And there's a reason for that. As it turns out, symbolic logic and set theory are both Boolean algebras. Boolean algebra is more general than either one of those. Okay, so what do De Morgan's laws look like in a Boolean algebra? Well, it says this. One is the complement of x plus y is complement of x dot complement of y. What's the dual of this statement? Everywhere I see a plus, I'll replace it with a dot and vice versa, and you get what? The complement of x dot y is the complement of x plus the complement of y. So that's its dual. Now, I'm going to concentrate on just proving this, and I say the proof of the dual, right, is just you take each of these statements over here and you write its dual, and that's the way the argument goes, all right? But what does this statement mean? The complement of this thing is this. Remember, we've dealt with complements before. All right, so it suffices to show what? That if I take this, x plus y, and I add this, x prime, y prime, I must get 1. Or if I take this inside thing, x plus y, and multiply or dot it with x dot y, I should get what? 0. So proving this is equivalent to proving these two statements. Okay, so now I'm going to concentrate on those two statements, and in particular, I'm going to look at the first one, which I've outlined in yellow, and I'm going to start over here, and I'm going to end up with 1. So here goes. This is equal to, and now what am I going to use? I'm going to use the distributive axiom. Okay? But I'm thinking of it as this. This element add x prime dot y prime. Now this is going to be the funky distributive axiom that we're not used to, right? What does the axiom say? That it's this, add the first, so it's x plus y add x prime, times what? This add the second, so x plus y add y prime. That's the second distributive axiom, right? And now what am I going to do? Well, I'm going to associate things differently and switch the order a little bit. So I'm going to use the associative axioms and the commutative axioms to get me. I could write this as x plus x prime, add y, or x, add y plus y prime. Now, what is x plus x prime? Well, the complement axiom says x plus x prime is just 1. And y plus y prime is just 1. So I use the complement axiom to replace those with the value 1. And then what can I do? Well, the bound law says 1 add anything is just 1. So 1 add y is 1, 1 add x is 1. So the bound law says that's just 1 times 1. But now 1 times anything is that thing back. So the identity axiom tells me that 1 dot 1 is just 1. And I'm finished. I started with this side and I ended with 1. Now I'm going to prove this second part, okay? And again, I'm going to start on this side and I'm going to end up with 0. All right, so let's start on this side. I have this. And now I'm going to use the distributive axiom again, but I'm going to think of it as this. It's this piece dot this sum. All right, so what does the distributive axiom tell me? That something dot a sum is this something, x prime, y prime, dot the first, x, add this, x prime, y prime, dot the second. Okay, so that, in fact, is the distributive axiom that we know and love. Okay, and now I'm here. What can I do? And the answer is I can use the associative axiom and the commutative axiom to move things around and regroup them, reassociate them. So I can combine the x dot x prime, what's left is y prime, and I can combine the y dot y prime, and what's left is x prime. But what is x prime by the complement axiom? Well, x prime is just 0. And by the way, so is y prime. It's just 0. So I get 0 dot y prime add x prime dot 0, and I got both those from the complement axiom. But what does my bound law say? It says 0 dot anything is just 0. So I use the bound law to call this 0 and call this 0. But now I know what? That 0 add anything is that thing back. What am I using? The identity axiom. And so I get 0 add 0 is just 0. And lo and behold, I have started with this side and I have ended with that side. So this is proven, right? So I prove this and I prove that. Hence, this is true. Now again, you can go through the same argument by dualizing the one I just gave. Or maybe you'd like to try it on your own. But those now are Demorgan's laws. Okay, and now I know them to be true. Well, that's all I'm going to talk about with respect to Boolean algebras. You should be all ready to do the next homework set. Good luck, stay safe, and bye.